All right, hey everyone, welcome back to our lecture series for linear algebra. Today we'll be starting chapter 6, and we're only going to spend 2 videos covering chapter 6, and this will be the last chapter that we're doing, so home stretch. And so chapter 6 just addresses the theory that we've developed over the course of the semester, but for vector spaces in general. So at the very beginning of the semester, we talked about vector spaces. Oh, we said that we were going to define vectors, matrices, matrix multiplication, that kind of thing, linear transformations, systems of linear equations, and then we just threw that word vector spaces out there. We kind of haven't mentioned it at all. However, the theory of vector spaces is kind of the whole point of studying linear algebra. So yeah, and so we'll start to see vector spaces in general starting now. Now, the great thing is that first of all, we are already familiar with one family of vector spaces, specifically Rn. We thoroughly addressed all of the theory of linear algebra for the vector space Rn and linear transformations between vector spaces Rn and Rm or whatever. We developed a whole lot of theory of matrices, but yet every matrix, right, was a matrix, could be viewed as a matrix transformation from Rn to Rm. If there was like an n by n matrix, right? Invertible matrices sort of went hand in hand with invertible transformations of vector spaces Rn and Rm, or Rn to itself, right? And so on. There's one last thing that we're going to do with orthogonal matrices and things like that. And so, but anyway, so we'll see all of that moving forward. But we have a very rich theory with one particular class of vector spaces. But fortunately, everything that we've said so far is far more general than just Rn. So the idea is, everything, what do we need from our discussion to generalize beyond Rn? Well, actually, as it turns out, there are precisely 10 properties of Rn that the entire theory depends on, and only 10 properties, which is kind of amazing considering we've had an entire semester of properties, right? And so let's go and investigate those properties. So the first thing that we're going to do is just give the actual definition of a vector space. So a vector space V is a set and two operations. So anytime anyone wants to specify a vector space to you, they have to tell you what the set is, what it means to do vector addition, and what it means to do scalar multiplication. So the set is the set of vectors, and then we have to have a collection of numbers, probably the real numbers, which will be the set of scalars. Okay, and then given those three objects, a set of vectors, a way of adding two vectors together, and a way of scaling one vector by a number, here are the properties that they need to satisfy. These are going to look very familiar, and actually, I hope that your impression of these properties is that it's like, duh, like these should feel very obvious, right? And so for example, I want addition. If I have a vector space, I should be able to add any two vectors and obtain something which is a vector inside of that vector space. In Rn, or in R2, for example, if I have the vector 1, 1, and I have the vector 2, 3, addition is defined component-wise. So we're looking at the vector 3, 4. This first property is just the observation that the output vector 3, 4 is also a two-dimensional vector. Yeah, that's Of course, right? This is what we are expecting. And so, right, and so this kind of property. So let's just go through them, the rest of them. U plus v will give you the same vector as v plus u. In other words, addition commutes. That's not necessarily true of multiplication, as we'll see in a moment. Actually, there is no notion of multiplying two vectors. But when you add two vectors, the order that you add them in shouldn't matter. Similarly, so that's the commutative property for addition. There's also associativity for addition, which is that if I were to add three vectors together, I can either add the first two, because right, vector addition is literally a binary operation. I can only ever add two vectors together at once. I can't add three in a row all at the same time, even though we do shorthand. That's true of just number addition. 3 plus 4 plus 5. If you were to go and evaluate that sum, think about what you're actually doing. You are either going to add 3 plus 4 first, or you're going to add 4 plus 5 first. You could also add 3 plus 5 first, but to do that, you'd have to switch the order somehow. So it would be like 4 plus 3 plus 5 like this, and then you can add your 4 to it, right? Addition is a binary operation. It only takes in two inputs and spits out one output. Vector addition is defined in the same way. However, vector addition also obeys the associative property, namely that I can, if I want to add three things together, I can either add the first two and then the third one to the sum, or I can add the first one to the sum of the second two, of the last two, right? That's the associative property. Again, these are very obviously true for vectors in Rn. Okay, number 4, you have to have a zero vector. In other words, I need a vector in my in order to call my space a vector space. I need to have the presence of a zero vector, which is a vector that I can add to any other vector and not change its value, or not change its identity. It will be the same vector. Right? I also need, property 5, I also need the existence of an additive inverse for every vector. So every vector needs to have some other vector in my vector space, such that when I add the two vectors together, if I add the pair together in either order, they mutually annihilate down to the zero vector, the additive identity. Again, these properties, we've seen all of these before, right? I've grouped them in two groups of 5 as additive and multiplicative properties. That's just the way that I remember it. So you can feel free to remember these however you'd like. Let's take a look at the multiplicative properties. Again, we have scalar multiplication. So scalar multiplication is a rule for multiplying a number or a scalar by a vector to obtain a new vector. And however your scalar multiplication is defined, it must be the case that when you scale a vector by a scalar, you need to obtain a vector that is also inside your space. So let's do 3 times 1, 1. 3 times 1, 2. Something exciting. By the definition of scaling a vector in R2, we're going to get 3, 6. And again, this first property is just the observation that 3, 6 is also a vector in R2. And in general, no matter what number I multiply by what vector in R2, of course, I'm going to get another vector in R2, right? But if that were not the case, then I would not be allowed to call whatever space I was working in a vector space, right? We need scalar multiplication to preserve vectors inside the vector space. Properties 7 and 8 are the familiar distributive properties. If I have a number times the sum of two vectors, I could, if I have a scalar multiple of the sum of two vectors, I could scale the vectors individually first and then add. Similarly, if I have the sum of two scalars times a vector, I could scale that vector by each of those two scalars and then sum. Those are both the distributive property for scalars and for vectors. There's also a notion of associativity of multiplication, which is if I have a product of two scalars times a vector, that product of scalars is a scalar and it's scaling the vectors. But what I could do is scale the vector once by one of the scalars and then scale the vector again by the other scalar. Okay? And then the last property is the existence of a multiplicative identity in terms of scalar multiplication. That's the number one. Now, this is assuming that we're working over the real numbers everywhere, so that the scalars that we're using are still real numbers, C and D, right? C and D can be any real number. However, there's only one real number with the property that when you scale a vector by that number, you get the vector back, and that's the number one, right? 1 times any vector should give you that vector back. Okay, good. That's a good place to be. Okay, great. So now, let's take a look at some examples of vector spaces. I'm going to start with some. So this is going to be the main point of our lecture. You're going to see some examples of things that are vector spaces that are believable, but also some things that obey all of the theory that we've talked about so far, but you would not have suspected it. Those will be later on. So, for example, Rn. Rn is the one that we know. I can't just tell you a set or whatever. Rn is the set of n tuples of numbers. But with what addition and what scalar multiplication? Okay, vector addition, where you add component-wise, and scalar multiplication, where a number times a vector scales every component of that vector. That is a vector space, and that's the one that we've used exclusively up until now. Now let's take a look at this M23 thing. This is the space of 2 by 3 matrices. Matrix addition is the addition that we're talking about. And we saw this as an example in like chapter 2 or something like that, where you can do like linear combinations of matrices, and you can scale matrices by multiplying them by a number. Those are the operations that we're using to define the M23 vector space. Sometimes you'll see this one written as like M and then just the numbers 2, 3, or like MNN for the space of n by n matrices or something like that. Okay. But it is a vector space because notice the behavior of either adding matrices or multiplying matrices is exactly the same as the behavior of adding or scaling vectors in R6. Right, and that was our trick. We were like, oh man, how do I find the linear combination of these 3 matrices? I'll just pretend that they're vectors in R6 or whatever, and then do a linear combination. Okay, so the theory of linear algebra still applies to matrices as if they were our vectors to begin with. Maybe a little bit less obvious is something, this is not the official name for this space, at least I don't think so, but I'm calling it T23. This is the space of linear transformations from R3 to R2. Well, every linear transformation is representable with a standard matrix. And if it's a transformation from R3 to R2, the standard matrix of that linear transformation is a 2 by 3 matrix. And so this is secretly basically the same space as M23. It behaves all the same way. However, we have to specify, what do we mean by the sum of 2 linear transformations? Well, what is a linear transformation? It's a way of sending one vector to another vector, one vector in R3 to a vector in R2. And if I want to add 2 of those transformations together, what I do is I just take the rule of assignment from one and take its output and add that to the output of the other rule of assignment, right? In other words, the sum of 2 vectors in that space, which a vector in this space is a linear transformation from R3 to R2. The sum of 2 of them is defined by just adding their rules of assignment. Similarly, if I wanted to scale a vector in this space, or scale a vector in the space, which is like scaling a linear transformation, what that means, what I'm really doing is I'm taking that rule of assignment and scaling its output by whatever that scalar is. Okay, that's how how vector addition and scalar multiplication are defined. And if you check with some actual literal like linear transformations from R3 to R2, write down their standard matrices and then ask what do these operations do to the standard matrices, and you'll find they're exactly the output of matrix addition and like matrix scalar multiplication. So these are secretly kind of the same vector space in some sense. Actually, there's a word for the sameness. It's called isomorphism. These vector spaces are isomorphic. But we're not going to talk about isomorphisms in our class. So, but they're essentially the same vector space, just with a different name and different context. Okay. The last one that's you can believe that this is a vector space because it's got like, addition and multiplication. The last one is one that we're going to spend a lot of time. We're going to spend a lot of time looking at n by n matrices in this chapter, and this other one, which I'm calling Pn. Pn is the set of polynomials with degree less than or equal to n. What does it mean to add two polynomials? Just add the polynomials. Okay, what does it mean to scale a polynomial? Just scale the polynomial. Okay, so I haven't written what vector addition and what scalar multiplication means, but like, so for example, x cubed minus 1 is a vector inside of P3. And if I were to add two of so if I were to do, so is x, whatever. X is a polynomial with degree less than 3. So it's inside this P3 vector space. If I were to add them together, I get x cubed plus x minus 1, of course. And by the way, that is a polynomial with degree less than or equal to 3. And if I were to scale my x cubed thing by 2, for example, so 2 times x cubed minus 1 is 2x cubed minus 2. And lo and behold, it is a polynomial of degree less than or equal to 3, right? So we're left with, and you can verify the other properties. Oh no, if I have to multiply a number by the sum of two polynomials, that number distributes. Yeah. I just did it actually with this example on accident. Anyway, so now, so you can believe, my point is that these are believable as vector spaces. What you should do if you're unconvinced or if you're uncomfortable with this general definition of a vector space, you should pause now and verify that all 10 properties hold for these two vector spaces. Don't worry about T23. That's just a fun rephrasing of M23. But do worry about M23. That you should be comfortable with the fact that the collection of all 2x3 matrices is a vector space under matrix addition and scalar multiplication. And you should be comfortable with Pn. So the collection, maybe just do it for P4, say, or P3 even. Okay, P3. The collection of polynomials of degree less than or equal to 3 is a vector space where vector addition is polynomial addition and scalar multiplication is like scaling polynomials by a number. I do recommend pause the video and verify those 10 properties. It won't take much convincing, I hope. Hopefully you've done that. Let's go and look at some more strange vector spaces. This is a sequence of vector spaces that we're going to talk more about in just a moment. I'm calling them fancy P, fancy F, C, and D. P is for just the set of all polynomials defined on the real numbers, which all polynomials are defined on all real numbers. So just the set of all polynomials in a single variable. Okay, that is a vector space. However, like, what is the well, I'm not going to say dimension yet because that's for the end of this video. But like, what is this vector? It's like an infinite, like x to the 15th is inside this vector space, but so is x to the 515th, right? And like all polynomials of any degree, that is a vector space, and the vector addition is add two polynomials together, and the scalar multiplication is just scale your polynomial by a number. That forms a vector space. You can check that it'll satisfy all 10 of the properties that we laid out in the last slide. Here's something even weirder though. The set of all real valued functions defined on R. Every single function you can think of that is defined on all real numbers, yeah, that is contained, or that vector space is in fact a vector space. What is what is vector addition? Well, you just take two functions that are defined on the entire number line, e to the x and sine of e to the x. Both are defined for all real numbers. How do I add them together? Just add them together. Function addition is the vector addition for this set. Okay. Scalar multiplication. How do I scale such a function? Just add a coefficient out front. And that just is what it is. You can check that also will satisfy all of those properties, right? If I have two real valued functions, f and g, and I add them together, I get a real valued function. If I take that sum and scale it by 4, okay, that is just going to give me 4 times the first function plus 4 times the second function. So it's distributive. And also, you do end up with an honest real valued function defined on the entire real number line when you're done, right? That was several of the properties. What is the zero vector? Zero vector is y equals 0, like f of x equals 0, the x-axis. Yeah, go and add that to any real valued function. Any real valued function. You will not change the function, like the output of the sum of those two functions is just the function that you started with. And if you want to go and scale a function by the number 1, multiplying a function by 1 does not change it. The number 1. Right? Okay. Sitting inside of that, so not every function that's defined on real numbers is continuous. For example, f of x, here's an element of that vector space. 0, f of x is 0 if x is less than or equal to 0, and 1 if x is greater than 0. It's this one. It's the one that has the whole negative real axis and the origin, and then it jumps up to 1 with an open circle, and then it's this. It's like a step function or something like that. That's a real valued function, and it's a member of this fancy F vector space. However, it is not a member of C. C is the set of continuous real valued functions. Now, every continuous real valued function is, of course, a real valued function. So C is somehow a subvector space of F. We'll show that in just a second. But it still is a vector space, right? If you add two continuous functions, you get a continuous function, and so on. Okay, good. D, by the way, is the set of differentiable functions, and every differentiable function is continuous, but not all continuous functions are differentiable. For example, f of x equals the absolute value of x. Absolute value of x is continuous on the entire real number line. It is not differentiable at 0, right? So that is a member of C, but not a member of D. So again, D is like a sub-vector space of C. Amazing. And they're all of these, by the way, will turn out to be infinite dimensional. But we don't have a notion of dimension yet. Again, I recommend pausing now to check these properties. That's for mostly for curiosity. You can probably make it all the way through the semester and final exam, taking my word on the fact that these are vector spaces, but you shouldn't do that at this point in your mathematical development. Don't take my word for anything. You should be able to prove it all the way down to the axioms. Okay. So yeah, take a second to do that. Hopefully you have. And now have two more. These are crazy vector spaces. Truly, I would say truly bizarre. So I'm going to do this bottom one first. Z sub 2 raised to the n. That is the set of all strings of length n of zeros and ones, or the set of all n-bit binary strings. When you add two of those things together, addition is going to be defined as the exclusive OR. So in other words, 0 plus 0, which is like false plus false, will return false. If A is false and B is false, then A exclusive OR B is false. 0 plus 1 is false plus true. That'll be equal to 1. 1 plus 0 is like true plus false. So either one, so exclusive OR, for those of you who haven't taken computer science, says that it'll take two inputs. If both are false or if both are true, then the output of the exclusive OR is false. And if precisely one of the two inputs is true and the other is false, then it will return an output of true. So these are both 1, 0 plus 0 is 0, and also 1 plus 1 is 0, right? Because both of the inputs were true, but it's an exclusive OR. It's one or the other. This is the one that they mean when they say, do you want pepperoni or sausage on your pizza? And you just say yes. No, invalid. They're not saying, do you want pepperoni or sausage? Like, do you want at least one of them? No, they're saying you can choose one or the other. Choose. That's what they mean. So this is the grammatical usage of the word or. Exclusive or. Okay. And multiplication in this vector space, scalar multiplication is like and. So if I'm going to multiply by we're working over, you can only scale by 0 or 1. So this is separate from using the real numbers as our scalars. We're only using zeros or ones as scalars. And if you scale by a 0, that's like saying no to the entire binary string. And if you scale by 1, you're saying, okay, yes, and whatever the binary string says. This collection, so this is mostly as an Easter egg for computer science people. The set of n-bit binary strings forms a vector space. You can check that this thing satisfies all 10 of those properties, and you can do all of the vector space theory that we've talked about using z2 to the n rather than r to the n. Okay, and now let me tell you my favorite one, my favorite bizarre example, which is, okay, the set of vectors is the set of positive real numbers. Okay, that's the set of vectors. So any number that is not 0 or less, anything that's strictly greater than 0. Addition, so those are what my vectors are. My vectors are positive real numbers. I'm defining addition as two numbers, when I add them together, is take like their product. So, for example, 0.1 plus 3 in this vector space is defined as 0.3. I did not say that incorrectly. This is the definition of this vector space. 0.1 plus 3 is equal to 0.3. Okay? That's the definition that we're taking. And let's take, so now what are the scalars? Scalars are all real numbers. and a number times one of my vectors. So a scalar times a vector, scalar multiplication, is take the vector and raise it to the exponent of the scalar. What that means, so let's do that. So I need a scalar. Let's do 4 dot, I need a vector, a positive real number, 0.1. Not afraid. So 4 times 0.01 is 0.0001. And 3 times 4, 3 times 4 is 64. Under this definition of addition and multiplication. Okay, so when we do that, we have to this satisfies all 10 of those properties that we listed in the previous slide. So for example, there is an additive identity. The additive identity is 1. I should say 1 equals additive identity. Because r plus 1 equals r. For any vector r in this vector space V, r plus 1 equals r. Okay. And the multiplicative identity is also 1. 1 times r is also r. So in other words, 1 plus r equals 1 times r in this vector space. You can check the laws of the distributive property and associative property that all hold. And so in other words, 100% of the theory that we've developed so far in this class works with this vector space. It's bizarre, like I said. Now, before we move on, I will remind you, most of our examples moving forward are going to come from this first collection because they're not super weird vector spaces. However, vector spaces show up as the natural context for the solution space for some problem all the time. Whatever problem that you're trying to solve, chances are there is a natural vector space that the problem sits inside of, right? We will mention these slightly stranger vector spaces as a little bit more weird examples, and I'll never mention these horrendous ones again because they're really confusing. Although, man, you should try working out some of the examples that we've talked about in this vector space, or do V2 or something, the two-dimensional version of this, right? And see if you can even come up with a meaningful way of doing that. Yeah, just as a really good exercise in abstract thinking. Okay, so let's actually say some stuff about it. If you're counting the slides on my bottom right-hand corner, it looks like, oh man, we just got started. No. Getting our feet wet with vector spaces is intimidating at first, but you're going to find that if you're willing to accept those 10 properties on any set and your definition on scalar multiplication and vector addition, then what specifically of the theory that we've developed translates? Let's take a look. So first of all, let V be a vector space, and let U be some vector inside of V, and let C be a scalar. Some things that weren't on that list but that are consequences, the scalar 0 times U is going to give you the 0 vector. That's true even in this gnarly vector space. 0 times R is like Okay, 0 times 3, because 3 is a positive real number, right? And 0 is a scalar. That's 3 to the 0, which is equal to 1, which we said was our additive identity. In other words, if you take the 0, if you multiply the 0 scalar by any vector, it returns the additive identity. This is obvious in Rn, but like think about it in terms of like M23, right? You have a 2 by 3 matrix and you scale that by 0. You will get the 0 2 by 3 matrix, right? That's what this is saying. And more, it's all that general stuff. Take 0 times any polynomial, you get 0. 0 times any real function, any real valued function defined on R. It's the 0 function defined on R, right? The additive identity. Likewise, if you take any number and you like any scalar and you multiply by the additive identity, you will still keep the additive identity. So that would be like trying to scale the 0 matrix or trying to scale the 0 polynomial. That's not going to happen. You'll never get away from the 0, the additive identity. Okay, try -1 times any vector. That will give you the additive inverse of that vector. Scaling, so the way that you check that is you just take a vector u, any vector u, so any 2 by 3 matrix, and add to that thing the scalar -1 times your vector u. So scale the vector that you've gone, and by vector I mean 2 by 3 matrix or polynomial or something like that. Scale it by -1. So for matrix, multiply all the entries by -1. For a polynomial, multiply all the coefficients by -1, right? And then add that to the original thing that you started with. You better get 0, right? But by the fifth additive property of vector spaces, if you have every vector has to have the existence of another vector whose sum, such that the sum of those two vectors gives you the additive identity. Well, here I found the vector. It's -1 times that other vector, right? Okay. And then the last one is, suppose it is that these are the only two cases that give you the additive identity. So if a scalar times a vector gives you the additive identity, then you're in case 1 or you're in case 2, one or the other. Right, either you were multiplying by the scalar 0, or you are multiplying some number times the 0 vector. And this is not an exclusive or. You can also do like 0 times the 0 vector, right? So like, yeah, this is like at least one of those is true. The mathematical sense of the word or. Okay. Another thing that we'll do is define subtraction as the sum so like u minus v is the sum of u and the additive inverse of v. Just so that subtraction is well defined and we can use the shorthand notation. You don't have to do that. You could just write -v everywhere if you wanted to. But -v is the additive inverse of v. Okay, next up we're going to talk about subspaces. So we mentioned subspaces all the time, and we're comfortable in working with subspaces in Rn by now, theoretically. Okay, think about what is a subspace of Rn. That was like a line or a plane containing the origin. We are going to have a much broader definition of a subspace of a vector space. In fact, a subspace of vector space is just a subset of the vector space satisfying all the properties of a vector space. In other words, if I had the set of all degree 3 or less polynomials, P3, and I subtract, and I inside of that space, I take P1, the set of all polynomials of degree 1 or less, so ax plus b's. Okay, that is a subspace because it's a subset, and obviously it also satisfies all the properties because Pn satisfies all the properties. We saw that, right? So subspace. But how do you check if like how do you is there do you really have to go and like someone hands you some specific subset, um, and you have so they give you a subset and they say, okay, is this a subspace? What are you gonna do? Check 10 properties? That's painful. So theorem 6.2 comes in on the clutch. We saw this before in whatever the section about subspaces was. I think that was the beginning of chapter 3. Where we basically said that as long as an arbitrary linear combination of vectors inside of your subspace remains inside of the subspace, then all of the properties of a vector space will be satisfied. That theorem, do you remember that theorem? It holds true for arbitrary vector spaces. In other words, if you hand me a subset, and we're going to do this as an example, you hand me a subset of some known vector space, all I have to do is check that an arbitrary sum of vectors inside the subset remains inside of the subset, and an arbitrary multiple of that subset remains inside of the subset. If that's true, then the properties hold. All the other properties are going to hold. By the way, for all the theorems in this section, we are not going to prove them. The proofs are almost identical to the ones that we did before because every proof that we've done up until now has only appealed to those 10 properties or theorems that we had proven that depended on those 10 properties of vector spaces in Rn. In other words, we've been kind of if this class has felt very analytical and like rigorous and logical, that was so that this step of generalizing to arbitrary vector spaces will be as painless as possible. No need for proofs because the proof is like literally the same. Just make sure that you know what U and V mean and that you started with a vector space, not just Rn. Everything will hold. Okay, great. So let's do an example of this. So W is going to be the set of symmetric n by n matrices inside of MNN. So this is the set of n by n matrices, square. A symmetric matrix is a matrix which is equal to its transpose. In other words, flipping Aij with Aji doesn't change the matrix. So it's like 1, 2, 3, 4, 5, 6. But then like, oh wait, I already messed it up. 2, 5, 6. 1, 2, 3, 2, 5, 6, 3, 6, 9. Notice taking that thing's transpose, flip across the main diagonal, you get the same thing back. Something like this, right? Something that's symmetric that way. So that is a subset of the set of all n by, okay, so in this case, it's the set of all 3 by 3 matrices, right? But I'm not appealing to 3 by 3 matrices. I want to do this in general. So any arbitrary n by n matrix, I have to show that the collection of matrices that are all symmetric of that same dimension is a subspace. Let me start by just adding two of them together. So suppose A and B are n by n symmetric matrices. That is, A transpose equals A and B transpose equals B. What I need to do is show that this is a subspace of W. Okay? So the question is A plus B symmetric? Is A plus B symmetric? Well, to answer that question, we have to take its transpose. So, sorry, instead of writing it, is A plus B symmetric? Let me ask it the same question, but differently. Is A plus B equal to A plus B transpose? Well, for that one, we can actually do something. A plus B transpose by a property of the transpose. Transpose is distributive over the sum of two matrices. If the sum of two matrices is, if you take the transpose of the sum of two matrices, that's the same as taking the sum of the transposes of those matrices. I don't know what theorem that was, but it was early on in our discussion of matrices, so probably chapter 2. It's a property of the matrix transpose, right? But notice A transpose is equal to A. Notice this is the thing we're trying to prove. And B transpose is equal to B, because A and B are both symmetric matrices. So in other words, if you take AB, take its transpose, you can recover, that is the same, sorry, if you take A plus B and take its transpose, that's the same as taking the transpose of A plus the transpose of B, which is the same as just A plus B. But that is the thing that we wanted to show. In other words, A plus B is in fact a symmetric matrix, which means it's inside of W, which means that given any two symmetric matrices, their sum is also symmetric. That was the first property that we need to show. Let's do the other one. The other one is kind of way more boring. So for any scalar, C times A transpose, by the same, whatever that theorem was that allows us to distribute the transpose over the sum, this is also equal to CA transpose. Yeah, you can just factor. You can imagine working this out, right? Scale the matrix A by C, then take its transpose. Every single entry of A has a multiple of C inside of it. Factor that thing out, and what's left is C times the transpose of A. Right? It's like, okay, it's kind of boring. But A transpose is equal to A because A is symmetric, right? And so this is just CA. But notice CA transpose is equal to CA, which means that CA is symmetric. So for any scalar C and any symmetric matrix A, C times A is also a symmetric matrix. We showed that. We showed that the sum also remains symmetric. And so since these two properties are satisfied by symmetric n by n matrices, notice the dimension of the matrix did not matter. We conclude that W is a subspace of the set of n by n matrices. Great. Verifying subspaces. Let's look at some other examples of subspaces. This will be fun. The trivial subspace, W equals the additive identity. And that's always going to be a subspace for really dumb reasons. Just take any, you have to verify these properties. Okay, take any two vectors inside of this subspace. We can only pick the zero vector. So pick it twice, add it together. Is it the zero vector? Yeah. So the first property holds. Take any scalar, multiply by the zero vector, or by one of our previous theorems. You'll get the zero vector back. And so you remain inside the subspace. There we go. Theorem 6.2 guarantees that the zero vector makes its own subspace of any vector space. That's fun. And in fact, every subspace is going to contain the zero vector for those reasons. So, yeah, but that's like the same as saying that every subspace of Rn contains the origin, right? We already knew that. And it turns out that property of subspaces is preserved, even generalizing vector spaces to super arbitrary. Okay, let's look at this gnarly chain now of subspaces. The set of real numbers. That is a subspace of the set of polynomials of degree 1. Why? Sorry, degree less than or equal to 1. Why? Because every real number is a polynomial of degree less than or equal to 1. Actually, it's a polynomial of degree 0 for a very dumb reason. And the set of polynomials of degree less than or equal to 1 is a subspace of the set of polynomials of degree less than or equal to 2. Because every polynomial of degree less than or equal to 1 is a polynomial of degree less than or equal to 2. Right? And you can imagine this is going to go on forever. And all of those are going to be subspaces of polynomials, of the space of all polynomials. No matter how big n gets, polynomials of degree less than or equal to n is always a subspace of the set of all polynomials. But every polynomial is differentiable and defined on the real line, so P is a subspace of D. But D is a subspace of C. The set of every differentiable function is continuous, right? And so that is a subspace, and of course it's a vector space, so it satisfies, so it's a subspace of the set of continuous functions. But every continuous function is defined on the real line, is a function. And so C is a subspace of F, right? You could actually go and there's a chain inside of here. If you do C1 is like the set of functions which are continuous and differentiable of course, and whose derivative is continuous. Then there's the space of twice differentiable functions, and then there's C2, which is the set of C is like C0. D2 is going to be like D is like D1. D2 is like the space of twice differentiable functions. Then C2 is the space of twice differentiable functions whose second derivative is continuous, and so on. And it goes chain reacts like all the way down. And P is a subspace of all of them. It's amazing, right? Okay. Anyway, so there are so many vector spaces, right? Oh, and like there's Rn, by the way. Right? Or I guess there's R sitting all the way at the bottom. Rn kind of goes parallel, like R2 is kind of here, and then R3 is kind of here. And these are the only ones that we've talked about. But there's like we could take everything that we did with real with n tuples of real numbers and turn them into polynomials. And all of those live inside the set of polynomials. And like polynomials, the space of all polynomials lives inside this infinite chain of differentiable and continuous some number of times functions. And all of those are inside of the set of real valued functions. And if you're wondering if there's like more going this way, oh yeah, there's like there's a lot of vector spaces out there. So I'll leave that to your imagination, I think. Okay, let's talk about linear independence and span for a bit. So again, right, the purpose of this video is to just take all the things that we know about vector spaces and say that they always hold. And so, yeah, that's all there is to it. The set of linear combinations of the set of vectors of a set of vectors S, v1 up to vk, is called the span of S. That's awkward. Denoted span of S. Okay, P2, that'll be the span of x, 1x and x squared. Notice every polynomial of degree less than or equal to 2 is some linear combination of these three vectors, which are themselves polynomials of degree less than or equal to 2. Similarly, you want to make any 2 by 2 matrix. Well, you can just do that. A 2 by 2 matrix is like A, B, C, D. Okay, do A times the first one, B times the second, C times the third, D times the fourth. Right? The span of these sets of vectors is the corresponding vector space. Okay? And then we have a cool theorem which just says that the smallest subspace containing a set of vectors v1 up to vk is the span of those vectors. And by the way, it's a subspace. We proved this. We proved that the span of a set of vectors is in Rn is a subspace of Rn. We proved that one before by showing that an arbitrary linear combination of vectors in Rn remained inside of remained inside of was expressible as a vector inside of that subspace. That again was when we were introducing subspaces, and so the proof for this theorem is the same as that other proof, right? The fact that it's the smallest subspace comes from saying, just imagine that there was another subspace that was larger. You will arrive at a contradiction, right? You'll find that. Imagine that there was a smaller subspace inside of it. That will be missing one of these vectors, and so it, in particular, doesn't contain the span, right? Anyway, in linear independence, similar to the concept of span, generalizes in the same way. So a set of vectors v1 up to vk in some vector space is linearly independent if the only solution to this equation, the linear dependence equation, is the trivial solution. That was how we originally defined linear independence or linear dependence, right? It was like, oh, if there's a non-trivial solution to this linear combination type thing, then that set of vectors is linearly dependent and it's linearly independent otherwise. That definition we just copy paste verbatim for larger or for arbitrary vector spaces. Okay. By the way, we had a condition for to check if a set was linearly dependent. That was, can you take one vector in your set, do an augmented matrix with that vector off to one side and the rest on the other side, row reduce, and find a consistent system with a non-trivial solution. Sorry, with any solution. If the answer was yes, then your set was linearly dependent. If the answer was no, your set was linearly independent. That process for checking linear dependence still works in arbitrary vector spaces. You just ask, can one of my vectors be written as a linear combination of the other ones? If the answer is yes, the set is linearly dependent. And then to find to show that this has a non-trivial solution, just do your linear combination, but then subtract the vector that you wrote as a linear combination from both sides. Its coefficient will be -1, which is non-zero, so there is a non-trivial solution to this equation. Okay, let's look at some linearly dependent sets. In this first one, notice 3 times x squared plus 3x minus 4 minus 5. This makes me nervous. Yeah, minus 5, I hope. Times 2x plus 1, 2x minus 1. Minus 2. Apparently there was a typo in this problem. Equals precisely 3x squared minus x minus 2. In other words, because we can write one as a linear combination of the other ones, right, that set is linearly dependent. Similarly, notice this vector, matrix, but I'm going to call it a vector because it is a vector inside of the vector space M32. That matrix is -2 times the first, which means that it can be written as a linear combination of the other vectors in the set. Granted, there's only one other vector in the set, but we can still do a linear combination of that one vector by scaling it by -2 to get this other vector, so the set is linearly dependent. It's even worse. In F, sine squared x and cosine squared x and cosine of 2x is also a linearly dependent set. The reason for that is because sine squared x minus cosine squared x. I might have that backwards. Let me check. I think it might be cosine minus sine, actually. I've written it, and now I'm definitely double guessing. I think it's cosine minus sine. Yeah, cosine minus sine. There's a double angle formula of some kind. Cosine squared x minus sine squared x equals cosine 2x. Well, you go 1 times this vector minus 1 times this vector gives you this vector. And that's a linear combination. Cosine of 2x is a linear combination of cosine squared x and sine squared x. So the set is linearly dependent. So if it asks us to determine whether 1 plus x plus x squared, and 1 plus x squared is linearly dependent in P2, how do we do it? We have to ask, what are the solutions to C1 times 1 plus x plus C2 times x plus x squared plus C3 times 1 plus x squared equals 0. What are the solutions to this? Okay. Now, before you sort of jump outwards, let's just expand out and refactor in terms of 1x and x squared. So if I write this as I could write this as C1 plus C1x. Sorry. C1 plus C3. Notice I distribute the C1 and the C3 and then factor the constant term. For x's, I can distribute the C1 to the x and write this as C1, and then C2 also has an x, so plus C2 times x. Distribute the C1 and the C2 to their appropriate binomials, and then factor the x term. Okay, and then the last one we can write as plus C2 plus C3 x squared equals 0. And now, when is a polynomial equal to 0? It is equal to 0 precisely when all of its coefficients are equal to 0. So there is a system of linear equations lurking here. I need C1 plus C3 to be equal to 0. I need let me make this a little bit more obvious. I need C1 plus C2 to be equal to 0. And I need C2 plus C3 to be equal to 0. Wait a second. I've solved this equation before in our class, right? This is all we have to do is solve the linear system 1, 0, 1, 1, 1, 0, 0, 1, 1, augmented with 0, 0, 0. Hopefully you'll believe that this row reduce, well, you don't have to believe me, just row reduce it. And you'll get 1, 0, 0, 0, 1, 0, 0, 0, 1, augmented with 0, 0, 0, which tells us that the only solution is trivial. In other words, C1 plus C3 equals 0, C1 plus C2 equals 0, and C2 plus C3 equals 0. The only real numbers, C1, C2, and C3, that satisfy all three equations simultaneously are 0, 0, 0, that triplet of numbers. But that's the trivial solution, and we already knew that that would be a solution. However, because it's the only solution, we say that the system is linearly, the vectors are linearly independent. And that's it. Notice, we could have done this much more directly by doing the trade-off. Trade off the first vector 1 plus x for the vector 1, 1, 0. Trade off the second vector for 0, 1, 1. And trade off the third vector for 1, 0, 1. Right? All I did was remove the x's or whatever and put coefficients in the appropriate spots. That matrix, when you put all three of those matrices together and ask whether the vectors are linearly independent, you jump right to this system of equations, right? It's the homogeneous matrix vector equation instead of doing it as like a linear combination of polynomials. So sometimes it's very notice we had that trick before when we were trying to find linear combinations of matrices way back in chapter 2 or whatever. We had the trick of, just pretend like they're vectors and then do what you know about vectors. Yeah. In fact, that when it applies, you should take advantage of that kind of trick. Okay, so the last topic that we'll discuss are bases and coordinates, because remember, in the past, up until now, the main strategy that we have to get a hold of a vector space or subspace is by grabbing onto its basis or any basis for it, right? That's how we identify a subspace. When someone says, describe this subspace W, pretty much if you just say it's the set of linear combinations of this basis, that's enough, right? So our definition for a basis is the same. It's a linearly independent spanning set. Basic examples, the standard basis for Rn and the standard basis for Pn. Standard basis for Pn is just like a set of monic monomials. So monic is coefficient of 1. Monomial means one term whose degrees are less than or equal to n. Notice, you want to make any polynomial degree less than or equal to n, you just write its coefficients times each of these things, and you'll end up with a basis you'll end up with that polynomial inside of Pn. Standard matrices, you can have a standard basis for the set of m by n matrices. You just put ones in each of the possible entries of your matrix and zeros everywhere else. Okay, so now let's talk about the coordinate vector. You've seen this definition before, but we'll remind you. So let B be any basis for V. Remember that every vector, we don't remember stating that every vector can be written as a unique linear combination of the elements in that basis. Operative word here being unique. Of course, a basis is a spanning set, so every vector can be written as a linear combination of the basis vectors. But the point of having a basis is that because it is a linearly independent spanning set, it is small enough that whenever you go to write a vector as a linear combination of those basis elements, the linear combination that you write is unique. It is the only way to write that vector as a linear combination of your basis vectors. If you're one thing that you can try is just do a simple case in R2, where you have a linearly dependent set that spans R2. Find more than one way to write some vector V as a linear combination of those basis vectors. You'll find there's actually infinitely many ways because you have a dependent system and free variable, blah, blah, blah. Okay. So suppose that B is a basis, V is the set of it is has some is expressible in terms of that basis uniquely with coefficients c1 up to ck. Then we call those coefficients the coordinates of v with respect to the basis b. We also say that the column vector v sub b, we call that the coordinate vector of v with respect to b. You've seen this definition before, although it's about to become much more relevant, especially in the next section. Okay, so we have another theorem which just says that if you have given a basis and k vectors inside of your vector space v, then the set of those k vectors is linearly independent if and only if the set of coordinate vectors for each of your vectors is a linearly independent set in Rn. In other words, what you do is take each of your vectors, find its coordinate vector. That is a vector in Rn. Notice it's just a column of n scalar, like real numbers. Well, by definition, that's a vector in Rn. This theorem is saying that one check for linear independence in an arbitrary vector space is by checking whether that collection of column vectors is a linearly independent set in Rn. So it's just another tool to add to our tool belt. And then the very last thing that we'll talk about is dimension. I've combined theorems 6.8, 6.9, 6.10, and the definition of dimension into this one theorem, the master theorem. It's because efficiency, I guess. So we start with V being an arbitrary vector space, and suppose that it has a basis that contains n vectors. So first of all, what we're going to do is define the dimension of V to be equal to n. Now you might think, wait a second, what if I had chosen a different basis? Okay, the next bullet point, I guess, is a generalization of the basis theorem. That is a generalization of the statement that every basis for Rn contains n vectors. Yeah, every basis for a vector space V that has a basis containing n vectors every basis of that vector space contains n vectors. It's called the basis theorem. That's that result. Okay, and then well, there's more that we can say, which is that every set containing more than n vectors in V, right? Every one of those sets is linearly dependent. If you take a basis and add even one more vector to it, then your set is going to be linearly dependent. Also, the contrapositive of that statement shows up in a different theorem, I think theorem 3.10, and it just says that if you have a linearly independent set, that set must contain fewer than, at most, n vectors. So n or fewer. Okay, so that's linear independence or linear dependence. And sort of the opposite notion to that is span. So no set of fewer than n vectors spans all of V. If you don't have all n vectors, then you don't span the entire vector space. There's just not enough vectors. And the contrapositive of that says that every spanning set contains at least n vectors. If you're going to span the whole vector space V, you need at least n vectors to do it. Fewer will not suffice. Okay. Now, okay, the next thing is, what if you had a set that contains exactly n vectors? Well, then that says if you know that it's either linearly independent or that it spans all of V, you get the other one for free. So any linearly independent set of n vectors also spans V, and any spanning set of n vectors is linearly independent. That's kind of nice. Also, If you have a set of vectors that is linearly independent, you can extend it so that it spans V. Or if you have a spanning set, so we know that has a lot of vectors in it, you can reduce it so that it is down to a set that's linearly independent. Both times when you do that, that process will obtain a basis for V of n vectors, right? Okay, great. A lot of facts that take digesting. Again, there's no proof. I mean, there's about 2-3 pages in the book of proof for all of these facts, but we're not going to go into it right now. Okay, so the question is, so let's do an example of find the dimension W for the vector space W of 2x2 symmetric matrices. Okay, 2x2 symmetric matrices. In other words, so the set of W is the set of, we'll do A, B, B, C, like this. After all, we're just asking that every matrix that we're looking at has this form. So we need to find a basis for this set, right? What does it mean to be a 2x2 symmetric matrix? It means that, first of all, you're a 2x2 matrix, and that if you take the transpose, you'll get something that's equal to the matrix that you started with. But the transpose of a 2x2 matrix is the matrix obtained by switching the 1, 2, and the 2, 1 entries only. That's it. If you want that to be the same matrix when you're done, then you have to ask that the 1, 2, and the 2, 1 entries match. And then we don't care about the 1, 1 or the 2, 2 entries at all. So so in other words, W is the set of matrices of this form. Let's write down a basis for it. Well, I can think of a basis that will work. Well, I want to write an arbitrary matrix in this vector space as a linear combination of some vectors. So how about 1, 0, 0, 0, 0, 1, 1, 0, and 0, 0, 0, 1? A, B, and C. That definitely spans this vector space. Do you see that? I can get any vector of this form by just doing A times the first one, B times the second, and C times the third. So in other words, this is definitely a spanning set, right? And that's why I wrote this. It's the span of, like, W is the span of these 3 vectors. The question is this set linearly independent? What do you think about that? Is the set linearly independent? So how do we prove it? We have to find what are the solutions to C1 1 0 0 0 plus C2 0 1 1 0 plus C3 0 0 0 1 equals 0. I guess equals the 0 matrix. So 0 0 0 0. What are the solutions to this? Now remember, we've been down this road before in this video. I don't want to go and like distribute the C's and then come up with a system of linear equations. Notice I could just send this over to the same question but in R4. I can write this as is the set 1 0 0 0 0 1 1 0 0 0 0 1 independent, linearly independent. Is that a linearly independent set? And you look at it and you think, of course. Go ahead and augment the matrix with where those are the columns. Augment that matrix with the 0 matrix, and then row reduce. It's almost row reduced already. But what you'll find is that the coefficients that you need in order to solve that linear system are precisely the ones where C1, C2, and C3 are 0. So this set is linearly independent. So this set is linearly independent. But wait, now we have a linearly independent spanning set. This is a basis for W. And how many vectors are in it? 3. So the dimension of W is equal to 3. Yeah. Again, this is the same kind of reasoning that we've been doing all semester, but with an arbitrary vector space. Notice it's all about like, I just threw a random subspace of M22, right? Could have been some random subspace of polynomials of degree 3 or less. Or, God forbid, it's some subspace of a bizarre metric vector space. That would be terrible. Okay, so now we want to extend 1 minus x, 1 plus x to be a basis for P2, knowing that the dimension of P2 is equal to 3. First of all, by inspection, we know that this set is currently linearly independent, right? Notice 1 minus x is not a multiple of 1 plus x. What are you going to do? Multiply one by negative, like multiply the second one by -1 to get the first one? No, because that will negate the 1, the constant term, right? And then it still won't be a multiple. So this is linearly independent already. So we just need to find another polynomial of degree 2 or less, such that any polynomial of degree 2 or less can be written as a linear combination of these guys. Now, we just need something that's not linearly dependent on the first two. So why don't we just there's a few ways that you could do this. Your suspicion is, I should just include x2, x squared into this set. Well, you could do that, but you don't know for sure that remains linearly independent. And in general, is there a strategy that will work? Well, you could. You could try that. So you could try that. So try 1 minus x, 1 plus x, x squared. It'll work. Unfortunately, that's just intuitive. You notice there's no degree 2 terms in each of these. So what else could you do? Well, I know of a basis for P2, namely 1x x squared. So if I take all 3 of those vectors, which are polynomials, and include them inside of this set, I'll get a gnarly set. 1 minus x, 1 plus x, 1 x, x squared. Okay. Now the question is, can I write all of these? So now I know that I'm spanning. Now I know that this set spans all of P2, because this set spans P2, right? I'm not going to lose the spanning property by adding more vectors into my set. No way, right? And so the question is, can I write how many of these guys can I write as linear combinations of the previous ones? Well, you can go and do it if you want. You can reduce the matrix 1, -1, 0, 1, 1, 0, 1, 0, 0. That has a free variable by inspection, including the 1 doesn't give us a spanning set because that's a linearly dependent set. You could do 0, 1, 0, but again, linearly dependent free variable. Look at that row of zeros. But notice, where did I get this matrix from? I guess I should be augmenting with the 0 matrix just to be careful. Where am I getting this matrix from? I'm sending this thing over to vectors in R3. So 1, -1, 0. Where the vector in R3 corresponds to its coefficients with respect to the standard basis for P2, right? Something like that. Okay. So again, because there's a free variable in this system, x can be written as a linear combination of the other two vectors. I don't know what the linear combination is. However, I could find it just by simply row reducing. I think we could probably do this by inspection. If you did 1/2 of the first polynomial and 1/2 times the second one, that'll be 1/2 minus 1/2 x plus 1/2 plus 1/2 x. The minus and the plus cancel, and the 1/2s add together to get 1. So there's that. And I bet there's a minus sign there. Yeah. If you do negative 1/2 the first one, plus 1/2 the second one, then 1/2 minus 1/2 is 0, and 1/2 x plus 1/2 x is 1x. So there you go. That's how we write the first two of the new vectors as linear combinations of the old ones. But now let's try the x squared one. Well, sending that over to R3 puts a 1 in that third entry. And that thing, if you row reduce, you'll get only the trivial solution. So the set remains linearly independent when we append x squared. And sure enough, that was our intuition. We knew that this would happen, but this is why, right? In other words, 1 minus, like any number times 1 minus x, any number times 1 plus x, and any number times x squared. Those three things, when you add them together and ask that you get the 0 polynomial, the only way to do it is if the three numbers that you multiply by were 0. The set has to be so the set is linearly independent. And now we know that it spans our P2 because we augmented with a set that spanned P2, and then we were able to reduce, like chop away at the redundant vectors. Great. Okay, that's enough for this video. So next time we're gonna start we'll just cover section 6.3, which will be all about change of basis. So we'll have you start off with one basis and you want to switch over to a different basis. There's a process for doing that, and so that will be the section of 6.3, which will be our last video. I will see you there.